You have probably heard about the idea to create a settlement on Mars and make the red planet a second home for humanity. Sounds visionary until you realize we'd need to overcome 5 impossible challenges. And there's a far better alternative. Why are we even looking spaceward? Well, Earth faces some serious problems. Climate change threatening not just coastal cities with rising seas, but also causing devastating heat waves, extreme weather events, agricultural collapse in many regions, mass species extinction, and destabilizing entire ecosystems we depend on. Add to this diminishing natural resources, pollution, accelerating biodiversity loss, and a growing population needing food and clean water. With these challenges mounting, some suggest we need a planet B, and Mars looks like our best option. But is it really? The allure of Mars is understandable. It's relatively close in astronomical terms, has a day-night cycle similar to Earth's, 24 hours and 37 minutes, experiences seasons due to its axial tilt, and shows evidence of having once had flowing water on its surface. There's even frozen water there now. These similarities have fueled imaginations from science fiction writers to billionaire entrepreneurs, all painting pictures of bustling Martian cities beneath transparent domes. But the devil, as they say, is in the details. Let's explore why terraforming Mars represents perhaps the greatest engineering challenge humanity could ever undertake. The Martian atmosphere is pathetically thin, less than 1% of Earth's pressure, and mostly carbon dioxide. Even if we vaporized every bit of frozen CO2 on Mars, NASA studies show we'd only reach 7% of Earth's atmospheric pressure. Not nearly enough for liquid water or breathing. To put this in perspective, Earth's atmosphere exerts about 101.3 kilopascals of pressure at sea level, while Mars manages a mere 0.6 kilopascals. Mountain climbers start using supplemental oxygen at about 30% of Earth's sea level pressure. On Mars, you'd need a pressure suit just to prevent your blood from boiling at body temperature, a phenomenon known as ebulism. Creating a breathable atmosphere would require importing massive amounts of nitrogen and oxygen, elements that are scarce on Mars. NASA's MAVEN mission discovered that much of Mars's original atmosphere was stripped away by solar radiation over billions of years and is now lost to space. We simply can't recover what's no longer there. Then there's the magnetic field problem. Mars lost its protective shield billions of years ago, leaving the surface bombarded by deadly radiation. Any atmosphere we create would be continuously stripped away by solar wind. Building a planet-size artificial magnetic field? That's technology we can't even conceptualize yet. Earth's magnetic field is generated by a dynamo effect in our planet's molten iron core. Mars' core cooled and solidified long ago, shutting down this natural protection. The radiation environment on Mars's surface is approximately 30 times higher than on Earth, equivalent to receiving several CT scans every day. Prolonged exposure would significantly increase cancer risk and cause cellular damage. Some scientists have proposed placing a massive magnetic shield at the L1 Lagrange point between Mars and the Sun, creating an artificial magnetosphere. The energy and resources required would be staggering. We're talking about manipulating electromagnetic fields across millions of square kilometers of space. This would be a multi-generational megaproject with costs that would dwarf the largest engineering projects in human history. Mars is also brutally cold, averaging minus 63 degrees Celsius. Without a thick atmosphere, warming the planet enough for liquid water is virtually impossible. And speaking of water, while ice exists at the poles and underground, we can't keep it liquid without solving the atmospheric pressure problem first. The planet experiences extreme temperature swings, from a relatively mild 20 degrees Celsius in summer at the equator to a bone-chilling minus 125 degrees Celsius at the winter poles. Heat distribution is inefficient without a dense atmosphere to carry it. Even if we managed to warm Mars, the thin atmosphere would cause most heat to radiate back into space at night. Some proposals suggest using orbital mirrors to focus sunlight on the polar caps, or importing greenhouse gases more powerful than CO2, such as chlorofluorocarbons. But both approaches require technologies far beyond our current capabilities to implement at planetary scale. And both would need to run continuously for centuries before seeing significant results. As if that weren't enough, Martian soil contains toxic perchlorates that would poison humans and most plants. Detoxifying an entire planet, another monumental challenge. These perchlorates make up about 0.5 to 1% of Martian surface soil and are toxic to humans even in small amounts. They interfere with thyroid function and can cause developmental problems. Plants grown in perchlorate-rich soil would concentrate these toxins, making them dangerous to consume. Removing perchlorates from soil on Earth is done through expensive bioremediation processes using specialized bacteria. Scaling this up to planetary levels would require trillions of liters of water, which Mars doesn't have in liquid form, and would generate enormous amounts of byproducts that would themselves need safe disposal. Additionally, Martian soil lacks the rich microbial life and organic compounds essential for Earth-like agriculture. Creating fertile topsoil across an entire planet would take centuries under the best circumstances. There's also a fifth challenge not easily solved by terraforming. Mars has only 38% of Earth's gravity. We've observed significant health issues in astronauts after just months in microgravity: bone density loss, muscle atrophy, cardiovascular changes, and vision problems. While Mars gravity is better than weightlessness, long-term effects remain unknown. Would children born and raised in Martian gravity develop normally? Could humans adapt over generations? We simply don't know, and there's no technological fix for a planet's fundamental gravitational pull. When we add it all up, we're facing challenges that even unlimited money and resources couldn't solve within many human lifetimes. These aren't just engineering problems, they're fundamental planetary limitations that no amount of technology can easily overcome. But there's one other planet in our solar system that could be transformed into a secure and sustainable home for humanity for centuries to come, at a fraction of the cost: Earth. Even with climate change, pollution, and resource challenges, fixing Earth would be infinitely easier than terraforming Mars. We already have breathable air, liquid water, a protective magnetic field, and suitable temperatures, none of which we'd have to create from scratch as on Mars. Consider the scale. The worst estimates for climate change suggest parts of Earth might become uninhabitable for humans. But even these worst-case scenarios would still leave our planet far more hospitable than Mars could ever be in the next 1,000 years of terraforming efforts. The Antarctic desert, one of Earth's most inhospitable regions, is paradise compared to Mars. Many of the innovations we'd develop for Mars, like atmospheric carbon management, sustainable water cycles, and soil remediation, would be directly applicable to solving Earth's environmental challenges. And we wouldn't need to worry about creating magnetic fields or surviving extreme radiation. The technologies we need most urgently, carbon capture, renewable energy, sustainable agriculture, water purification, are precisely the ones that would help maintain Earth's habitability. Developing closed-loop life support systems for theoretical Mars missions could revolutionize resource efficiency on Earth. And crucially, the cost difference is astronomical. Estimates for Mars terraforming start in the quadrillions of dollars and span centuries or millennia. For a tiny fraction of that cost, we could address Earth's environmental challenges within decades. The truth is, if we ever develop the godlike abilities needed to terraform Mars, we'd be far better off applying that knowledge, technology, and resources to fixing our own planet first. The only downside? We'd lose our perfect excuse to ship off that one neighbor who won't stop mowing the lawn at 6 a.m. on Sundays. Mars will remain an important scientific destination, teaching us about planetary evolution and possibly early life. robotic exploration, and even small research outposts may be feasible in our lifetime. But as a second home for humanity, the red planet is a red herring. Our remarkable blue marble, despite its problems, remains the only place in the known universe perfectly adapted for human life. Perhaps our destiny isn't to spread across the stars, but to become better stewards of the extraordinary world we already have.